In this video, we'll take a look at section 1.3 notes, rates of change and behavior of graphs. So we want to be able to find the average rate of change of a function, use a graph to determine where a function is increasing, decreasing, or constant, and also use a graph to locate local and absolute maxima and local minima. So on an average rate of change, a rate of change describes how an output quantity changes relative to the change in an input quantity. And the units on a rate of change are output units per input units. So think about the linear functions that we've graphed so far. The rate of change is the slope, and the slope is the same between any two input values. It's a constant rate of change. So average rate of change describes basically the slope between any 2 points on a nonlinear function. So the average rate of change is defined between two input values is the total change of the function values, the outputs, divided by the change in the input. So the notation is a little bit different. This we have delta y over delta x. That means the change in y over the change in x is equal to, if you have 2 points, instead of x1, y1, our coordinates are x1, f of x1. Remember, if it's a function, f of x notation replaces y. Your second point is x2, f of x2. Then the slope between those 2 points, or the average rate of change, is the difference in y-coordinates, in this case f of x2 minus f of x1, over the change in x-coordinates, x2 minus x1. And a reminder, when we label the units, it's the output per input. So let's take a look at some examples. The first one is computing average rate of change from a table. So the situation modeled by the table is after picking up a friend who lives 10 miles away, Anna records her distance from home over time. The values are shown in the table below. Find her average speed over the first 6 hours. So we've got the first 6 hours is from when Anna starts to the 6th. So she's traveled between 0 and 6. She's traveled a total of 282. So what we do is, since this is hours, this is miles, to find the average rate of change, think of this as a function of having 2 points. We have the point 0, 10, and the coordinate 6, 282. So I want to find the change in miles, 282 minus 10, over the change in time, hours is 6 minus 0. And we're going to label miles, hour. So when we find our answer, we're going to label it in miles per hour. So we take the 282 minus 10, which is 272, divided by 6. I'm going to go ahead and put it in the calculator. Just open a calculator real quick. 272 divided by 6 is about 45 1/3, or 45.33. miles per hour. All right, so that's her average rate, her average speed. So you may also, besides being given values in a table, you might be given a function in graph form. So our next example is, how do you compute average rate of change from a graph? So if we're given the following function g, find the average rate of change on the interval from -1 to 2. So what we're trying to find, these are given in x values or t time values. When t is -1, the y value, or the function value, is 4, g of t. To 2, when the function value t is 2, then g of t is, from the graph, 1. So I have that when t equals -1, g of t, g of -1, is equal to 4. When t is equal to 2, g of 2 is equal to 1. So I want to find the average rate of change using the formula. It would be g of 2 minus g of negative 1 over 2 minus negative 1. So the y value, g of 2, is 1, so I get 1 minus g of 1, which is 4, over 2 minus a negative 1, which is 2 plus 1. I end up with negative 3 over 3, which equals negative 1. So the average rate of change over the interval is negative 1. So if you were to draw a straight line in between these 2 points, then the slope of that straight line would be negative 1. All right, next example, computing an average rate of change for a function expressed as a formula. So notice that you're given compute the average rate of change of f of x equals x squared minus 1 over x on an interval from 2 to 4. So you're giving the x values, the x interval 2 to 4, but we don't know the y coordinates that go with them. So we know that when x equals 2, we can find f of x. So we substitute f of 2 into the formula. We get 2 squared minus 1/2. So that would be 4 minus a half. 4 minus 1/2 is 3.5. Then when x equals 4, f of 4 is equal to 4 squared minus 1/4. 4 squared is 16. 16 minus 1/4 is 15 3/4. So in order to find the average rate of change, we're going to take f of 4. This time it does matter. You have to take the f of 4 minus f of 2 over 4 minus 2. f of 4 is 15 3/4, or 15.75, minus 3.5, 3.5, divided by 4 minus 2, which is 2. So I'm going to go ahead and put that in the calculator. And again, I'm just using a scientific calculator, or really just the calculator on the computer. So 15.75 minus 3.5 is equal to 12.25, divided by 2 is equal to 6.125. If you need that converted into a fraction, that's 6 1/8. And if you need it as an improper fraction, 6 times 8 is 48 plus 1 is 49/8. So you can express your answer. It depends on what the homework manager is looking for, but you can express it as a decimal or an improper fraction. All right, so average rate of change is basically the slope between any 2 points on a nonlinear function. And if you took the same nonlinear function, let's take a look at the graph above. If we pick 2 different points, let's say we went from 0 to 2, your rate of change would be different. So the average rate of change, because if you pick 2 different points, you're going to get a different average rate. All right, the next part of this section is behavior of graphs, where graphs are increasing, decreasing, or constant, and relative maximum or minimum values. So we have a function f of x, x to the third minus 12x, graphed below. So notice this graph goes forever in each direction. So the domain of this function is negative infinity to infinity. It's increasing for part of that, decreasing, and then increasing again. So a function is increasing, we read left to right. As the x values increase, the f of x or y values increase, and the average rate of change is positive. So this portion of the graph, reading from left to right, is increasing until you get up to this very top. Then it's neither increasing or decreasing. Then our function is decreasing. As your x values increase, your y values or f of x values decrease. So the average rate of change is negative. So on the other side of negative 2, our function is decreasing until it gets here, and then it's neither increasing or decreasing. And then after that, our function is increasing again. So if we were to write the intervals in which for which our function is increasing or decreasing, we use interval notation from left to right, and we describe x values where the graph is increasing or decreasing. So since this graph is increasing to here, the x values are from negative infinity up to negative 2. So this graph is increasing from negative infinity to negative 2. At negative 2, it's neither increasing or decreasing, so we use an open interval. Then it's increasing again from 2, but not at 2, so it's an open interval, to positive infinity. And notice we're using values of x, negative infinity to negative 2, 2 to infinity, and then we put a union sign in between the two. The graph is decreasing from negative 2 on the x-axis to 2. So we use an open interval again, negative 2 to 2. So that's where our function is decreasing. So when you're describing increasing and decreasing, when you're at, this is called a local maximum, this is a local minimum, your graph is neither increasing or decreasing. So again, you use an open interval. It's not in this particular graph, but you can also have a constant rate of change. As x values increase, y values remain the same. So your graph would be neither increasing or decreasing. It would be a horizontal line, which would be constant. All right, so what happens at these 2 points where our graph changes? So if our graph is changing from increasing to decreasing, that value is called the local maximum. The local maximum is the y value, or the function value f of x. So there's a local maximum of 16, it's not a coordinate, and it occurs at the value x equals 2. A local minimum is when your function goes from decreasing to increasing. A minimum is the value of f of x at the x value. So the local minimum is negative 16, and it occurs at x equals negative 2. So those are how we express, they're not intervals, they're not coordinates. And that's how we express local maximum and local minimum, the function values, and then where it occurs. Then there's something called, these are local, and absolute maximum or minimum is the greatest or smallest y value over the entire domain of the function. So in this function, our y values, this goes to infinity. The smallest absolute minimum would be negative infinity. The absolute maximum would be positive infinity. But there are local maximums and minimums between those. So just a general note, to put this in mathematical terms, f is increasing on an open interval if f of b is greater than f of a for any two input values, a and b, in the given interval, where b is greater than a. And I'll leave you to read the mathematical definitions of these as long as you're able to use them. So let's take a look at a couple of examples. Consider the function graphed at the right. Join multiple intervals with a union. So we want to first of all give the intervals where the function is increasing. So this function is constant, then it's decreasing, constant, increasing, decreasing. And it changes at each of these values of x. So our function is increasing in only one place. And we use the x value from 5 to 7. And we use an open interval 5 to 7. So our interval is increasing from 5 to 7. Where is our function decreasing? Well, we have a value decreasing from x equals 1 to 2, the open interval from x equals 1 to 2, union, because it's decreasing again, from 7, and this goes on forever, so it's also decreasing from 7 to infinity. Then last, give the intervals where the function is constant. So the function is constant if we consider this going on forever to the left, from negative infinity to 1, open interval on infinity, union, it's constant again from 2 to 5. All right, last example. Consider the function in the graph to the right. The function has a maximum of something at x equals something. The function has a minimum of blank at x equals blank. So the maximum and minimum are the y values. So the maximum and minimum, in this case, we're looking at local. So this is a local max, and the y value is 2. So the function has a maximum of 2 at x is equal to negative 3. The function has a minimum of the y value, negative 2, at x is equal to 1. And where is the function increasing and decreasing? Well, our function is increasing from negative infinity to 3. Again, it's increasing from at 1 to infinity. Then our function is decreasing between negative 3 and 1. Oops, I put a negative here, negative infinity. All right.